complex x over x. This function here is analytic in a cut plane. Okay, and there's a cut that begins at the point -1, and it goes all the way out to minus infinity. Okay? This function is an example of a function of Stieltjes. Okay, function of Stieltjes. And the pades, remember a pade is a polynomial divided by a polynomial. Okay? And what happens is that, so when we convert this into a sequence of pades, say Pnn, or Pnn plus 1, this is the main sequence of pades. You notice here I have plotted the Pnn's, or given the numbers for the Pnn's. This is the Pnn plus 1's. That's the diagonal sequence. You notice there's a polynomial in the denominator, and that polynomial has poles. And those poles are becoming dense on this cut. Okay? So the pades know that the cut is there. The question is, in what sense? What do you mean by saying that the poles are becoming dense on the cut? The poles, okay, and this is a technical word that mathematicians use. You say that the poles are mocking up the cut. Okay, whatever that means. Okay, it's hard to make that really precise, but this is where the poles are. Okay, and as you go to higher and higher polynomials, you have more and more poles becoming dense on this line. Okay, and the pades converge for all complex x except on this cut. So they converge, the pades converge everywhere in the complex plane for all complex x except for negative x, which is absolutely fantastic. Okay, so the Taylor series only converges here. That's where the Taylor series converges. But when you convert the Taylor series to a sequence of pades, they converge everywhere. So for example, if you pick that value of x, and you take the pade sequence, it comes closer and closer and closer to this point. Furthermore, on the real positive axis, and you'll notice that I evaluated the pades at the point 1/2 inside the radius of convergence, inside the circle of convergence, and at 1 on the circle of convergence, and at 2 way outside the circle of convergence. The pades on the real positive axis have a wonderful way in which they converge. You notice that the pade sequence converges as 2 separate sequences. This converges by going down. Okay, it converges in a monotone fashion downward. This sequence converges up. Okay, and they meet in the middle. So the pades are fantastic. If you had the Taylor series for log of x over x and you actually tried to sum the Taylor series, you belong in an insane asylum. Okay, you could sum millions of terms. Okay, it's a slowly converging series. Okay, but if you convert it to the pades, just a few pades know what the answer is going to be. And furthermore, since you have an oscillating sequence, you can Shanks the sequence and get even better convergence. Okay, so it's really wonderful. Okay. And yesterday, you had an exercise to use pades for the Stieltjes series. Okay, this is this famous Stieltjes series, -1, this one right here, minus x to the n times n factorial, okay, which is a wildly convergent series. And yet, when you calculate the pades, they do exactly the same thing. The nn pades are converging downward toward the answer, the n plus 1 pades are converging upward toward the answer, and here's the answer. Okay? It's really nice, really wonderful. Okay? And this is at x equals 1. This is at x equals 10. Okay? So you wouldn't think that at x equals 10 you could sum that series. No. Each additional term that you have in that series gives you a new pade which is even closer to the answer, and you can get arbitrarily close to the answer. Okay? All right, so this is one last example that I'm going to show you. This is an example where nothing is known. Okay? All I can show you is the numerical data, but this is not a series of Stieltjes, and therefore it doesn't belong to the class of functions that are understood at a rigorous level. However, there's nothing to stop us from doing a numerical experiment. And there's a very, very famous series, which is this series here. This is the series for gamma of x. So as x goes to infinity, gamma of x is approximated by the following function. It's approximated by x to the x minus a half, e to the minus x squared of 2 pi. Okay, and that's called the Stirling. This is the Stirling. That's the Stirling approximation to the gamma function. Okay, but it is followed by a series. Okay, and the series has the form 1 plus 1 over 12x plus 1 over 244x squared. These are very famous numbers. Next one is negative, and the next one is negative, and so on. Okay, and this is a divergent series. Okay, you may not know this series. You may only be familiar with that approximation, which is a very accurate asymptotic approximation, but this is even more accurate. Okay, and what you can do is take this and divide it by that and pade this series. Okay, now this series is not a series of Stieltjes, as you're going to learn. Okay, turns out that a series of Stieltjes must alternate in sign. Okay, and this series is not alternating in sign. So right away you can see it's not a series of Stieltjes, and therefore nothing is known about it. Okay. Nevertheless, if you use pade theory to convert that series into a ratio of polynomials, and you plot the polynomials, you see this wonderful convergence. Just fantastic convergence. You want a PhD thesis topic? What? That's it. Why does it work? I have no idea why it works. Okay? So they're really quite impressive. Okay, so what I would like to do, I'm going to skip this for the moment. Maybe I should, yeah, I'll leave this up. So, so what I want to do today is I want to show you where these divergent series come from and why they appear very, very naturally in essentially all contexts. And I want to show you the simplest way in which they appear, and I want to explain to you what is meant by a divergent series, like this series. This is a very famous series. This is the Stirling series. This is the Stirling approximation to the gamma function. And I want to explain to you what an asymptotic series is. Okay, so let's begin with that. Okay, okay. Now remember, I explained to you an asymptotic relation. Okay, so when you say that you have a function f of x, and it is asymptotic to g of x as x goes to x naught, which could be infinity, could be anything. Okay, what you mean is that the limit as x goes to x naught of f of x over g of x is 1. Okay, that the ratio of f to g approaches 1 as x goes to x naught. this is what you mean by an asymptotic approximation. Okay? And the reason that this is a non-trivial relation is that f does. Let me ask you a question. Suppose you know that this is true. Is this true? Is f of x approximately equal to g of x? It's not entirely clear what that symbol means, but you know, is the difference between f and g getting small?
No.
Say it again.
No.
Not necessarily. Indeed, you know, remember x squared plus x is asymptotic to x squared as x goes to infinity. So the difference between the two is becoming infinite. Okay? The difference between these two guys is becoming infinite as x goes to infinity, and yet they're asymptotic. Okay, so so normally when we do an asymptotic approximation, we generally think of f of x as being some very complicated function, a function which you might find in a book having a fancy name like Bessel. Okay, and this typically is some much simpler function. Okay, and this is the function that is an asymptotic approximation to that function. Okay, usually that's how we use an asymptotic relation. Okay, and asymptotic relations are useful because generally what you do to both sides of an asymptotic relation keeps this relation asymptotic. Okay, so you can integrate both sides or differentiate both sides usually. Okay. All right. Now, what is an asymptotic series? Okay, so suppose you see something like this. F of x is asymptotic to the sum from n equals 0 to infinity of a sub n x to the n as x goes to 0. Okay? This is an example of an asymptotic series. Okay? This series could be divergent. So it could be a divergent series. But what does it mean to say that this series is asymptotic to that function? Oh, by the way, remember that if f is asymptotic to g, then g is asymptotic to f. Okay? Doesn't matter whether f is on the left side or on the right side. It doesn't make any difference. Okay? And in this limit, f over g and g over f doesn't make any difference. Okay? All right. So what does this mean? This means that if you take f of x and you subtract off the first n, the nth partial sum of this series, okay, which is a sub n x to the n. Okay, so this is just the sum of a finite number of terms in that series. Okay, then this is asymptotic to the next term in the series as x goes to 0. Okay, this definition doesn't say anything about whether or not that series is a convergent series. It merely says that if you take the first n plus 1 terms and form a partial sum of the series, that partial sum is getting very close to f. In fact, we know exactly how close. It's this close. Okay? And this is true for all n. So this is the definition of an asymptotic series. Okay? Another way of saying this, of course, is that if this is asymptotic to that, then I can use this, I can write down this limiting process, right? And what I know is that the limit as x goes to 0 of f of x minus the sum from n equals 0 to infinity, a sub n x to the n, over x to the n plus 1, x partial sum, okay, over x to the n plus 1 is equal to a sub n plus 1. Okay? So therefore, this is the way to calculate, if you could calculate this limit, this is the way of calculating the nth term in the asymptotic series. If you knew this function f of x, you could write down this process. You could take this limiting process over and over and over and calculate all the terms in the asymptotic series. So the asymptotic series coefficients are unique. Okay, this is true for all n. And you notice in this definition, I emphasize, we never said anything about whether the series is convergent or divergent. Okay, now you have a question.
Well, an plus 1 shouldn't be 0. Yeah?
Sorry?
An plus 1, the n plus 1 term of a shouldn't be 0.
No, it might be. If this is 0, then you just go to the very next term in the series. In fact,
Yeah.
in general,
But nothing.
let me show you, there's nothing, a given term in an asymptotic series could be 0, in which case nothing can be asymptotic to 0, right? So it would be asymptotic to the next term in the series, okay? So if a sub n for some n happens to be 0, perfectly okay. Okay, then it can't be asymptotic to 0, so it's asymptotic to the next term in the series. That's all. Okay.
What if there's no next terms?
Yeah, then there's an equality. Okay, it's not asymptotic, just equal. Then the difference between f of x and the first n terms in the series is 0. We're not so interested in that. Okay. What I want to make sure you understand is the difference between an asymptotic series and a convergent series. So the asymptotic series this is a much more general behavior of a series than if you just have a machine that's generating arbitrary series, what's the chance that any of these series will converge? 0. Chance of having a convergent series is essentially 0, right? Set of measures 0. This is the general case for series. Okay, so you're walking down the street, and a guy comes up to you and he says, I have a series. I have the following series: minus 1 to the n, n factorial x to the n. Okay, I have that series. And he says to you, is that an asymptotic series? What do you say? Perfectly straight question. What do you answer?
Could be asymptotic to something.
You're getting there. Okay. Let me tell you what you say to the guy. But you're a very polite person, so you said it nicely. You tried to put it in positive terms. What you say to the guy is, that's a stupid question. Okay? Because a series, this question here is not a meaningful question. Okay. Do you notice in the definition I gave you of an asymptotic series, the function f of x appears in that definition. Okay? This is the definition here. And you cannot say that a given series, or it doesn't make sense to say that a given series is an asymptotic series. That's not a useful statement. The only useful statement is that this series is asymptotic to this function. Okay? In fact, what you can show, now let me continue on what you just said, okay, because what you said was correct. Okay? Given a series, I can always find a function to which that series is asymptotic. This is true for any series, period. Okay, so you just make up an arbitrary series with arbitrary coefficients. That series will be asymptotic to some function. Furthermore, there even exists an analytic function. That means a differentiable function in the sense of complex variables. There exists a differentiable function, an analytic function, to which that series is asymptotic. You can construct such a function. Okay? So asking if a given series is asymptotic, it's not an absolute inherent property of a series to be asymptotic. Okay? Because there always exists a function to which it's asymptotic. In fact, there always exists an infinite number of functions to which that series is asymptotic. Okay? Yeah?
Do you mean that every year?
No, asymptotic, things are only asymptotic in a limit. Okay, as x goes to 0. Okay, as x goes to 0. So this series is so there exists not just one, but an infinite number and even an analytic function to which this series is asymptotic. So asking whether a series is asymptotic is an empty question. You know, it's like saying, am I alive? Well, obviously, if you were able to ask that question, you're alive. It's not a useful question, you know. You get a question like that when you go to a nice restaurant, you know. You sit down at the table and the waitress or waiter comes over and they say, how are you today? Well, you know the answer to that question. If I weren't well, I wouldn't be going to your restaurant. So that's the first thing to remember. Now, the reason why someone might ask a question like this is that if we are dealing with a convergent series, it does make sense to ask, is the sum of a sub n x to the n a convergent series? Okay, this question is a meaningful question because convergence is an inherent property of that series. Okay? Convergence is not a relative property, but asymptotics is a relative property. It establishes a relation between a function and a series. Okay? In this statement here, this is a relative statement. This series is asymptotic to that function. But convergence is a property of a series independent of any other function. So if somebody gives you a series, you can run a convergence test and you can answer yes or no. This series converges or it doesn't converge. Okay? And if it converges, you can find the function of x to which it converges. It may converge rapidly or slowly, but if it's convergent, then it converges to a given function, and you can find out what that function is. Okay? Whereas over here, you can construct a function, but you can't construct a unique function. So again, a function has a unique asymptotic series, but a series could be asymptotic to many different functions. Yes?
So this may sound like a very stupid question, but is divergence an inherent property of a series?
Sure. We can test that a series diverges, but once it diverges, we can answer no to this question.
And that means
Okay, so divergent. All divergent means is that the answer to this question is no. Okay, but once we establish that the answer is no, it doesn't. It's a useless question to say, you know, okay, it's a divergent series, but is it asymptotic? Of course it's asymptotic. It's asymptotic whether or not it's convergent or divergent, because every series is an asymptotic series. Okay? Now, so the question is, okay, so any further questions about this? Yes.
When you say analytic, do you mean analytic in zero?
Analytic, no, not analytic at 0. Okay, so it's a function that is not analytic right at the point 0. Okay, it's not analytic at the point 0, but analytic as you approach 0. So, you know, this is a limit as you approach 0, okay? And if I wanted to make this precise, I might say as we approach 0 plus, which we're going to make that more precise later on. But away from 0, it will be analytic. At 0, it is not analytic, not necessarily analytic.
But
In fact, it would be very unusual if the function, if this were a divergent series. We know that the function cannot be analytic at 0. Okay,
And
we know that.
it also can have some cuts.
Sure, sure.
So-
There could be some cut over here, something like that. Okay, so analytic in a neighborhood of 0, but not necessarily at that point. Okay, not analytic in a 360-degree wedge, and this is something that is what you are talking about. Okay, which we have to talk about. It's very, very important. What you are talking about is something called Stokes wedges. So it is analytic in some wedge. Okay, I haven't made it precise yet, but it is analytic in some wedge that comes down to 0. Okay, but typically not a 360-degree wedge. But this would be the wedge in which that function is analytic. Okay. This is the complex plane. This is the complex x plane, and this is 0 over here. Okay. Now, one last remark. There's nothing here. I mean, I considered the special case of a function having that form. Okay, but it doesn't have to have that form. It could have the following form: x minus a. Okay, in which case this is an asymptotic series as x approaches a. Okay, we have an immediate generalization. And furthermore, the terms in this series do not have to have integer powers of x minus a. Okay, this could be say x minus a to the power gamma to the n. This could be a fractional power of x minus a. So we could have lots of powers. Doesn't have to be integer powers. Okay, yeah.
Should this step to be constant?
Sorry.
No. Should this step in series constant between
The consequent step on power of x.
No, it doesn't have to be. I mean, this in general could be some function of n here. Just some sequence of numbers. Okay, they don't have to be integers. They could be, half integers. They could be skipping over. They could just be some sequence of numbers. Okay, and it doesn't make any difference. Okay, and if we are talking about as x goes to infinity, then this would be a series of the form 1 over x to the n. Or it could be 1 over x to the alpha n. Okay, or something like that. Okay, so it could be, and it doesn't have to be a regular series of numbers. It could be just a sequence of numbers getting bigger and bigger and bigger. Okay, this is the form of this series right here. This series is asymptotic to gamma of x as x goes to infinity. And now you understand what I've written down here. Okay? Any questions about that? Okay, so now we get to the good part. How do asymptotic series arise? Okay? And they arise all the time. It's just a universal thing. And I would like to give you, I'd like to work through an example, and I don't know if we can completely finish that example because this is so rich. Okay, but I'm going to try. Suppose someone comes up to you and says, I have a differential equation that I'd like to solve. Okay, And the differential equation is x cubed y prime prime equals y. I'm choosing this equation because we can actually work right through the equation and get the answer. And the person says, I would like to know how the solution to this differential equation behaves near x equals 0. So I would like to perform, I mean, we're not going to try to solve that equation. That's too hard for us to solve. But I would like to perform a local analysis near x equals 0. Okay, now, Sarah, you taught differential equations, and you said something about series solutions. Okay, so let's just talk a little bit about what is the rigorous known theory of linear differential equations. Okay, so suppose you have a differential equation that is second order, but it doesn't have to be second order. This is true for nth order linear differential equations. So here is an nth order this is a second order linear differential equation. What I'm going to tell you is in general true. Okay? The first thing that I will do is put this equation into, different people call it different things, say normal form or something like that. Okay? So I can always divide by the coefficient of the highest power of x. Okay? So without any loss of generality, I divide by a of x. And now the equation becomes, say, a of x, and this becomes b of x. Okay, now we want to solve this equation, and we want to know the behavior of this equation near, say, x equals x naught. How does y of x behave near x equals x naught? Okay, now there are exactly three possibilities. Three possibilities. The first is that suppose a of x and b of x are analytic near, that means in a circle of some radius, about x equals x naught. What do we know?
Behaves like an oscillator. I mean, if
no. Well,
if,
no, I mean, we're talking, like, we're trying to write down solutions to this equation, and we're trying to write down the general solution to this equation. So we know the general solution is a linear combination, since it's second order, linear combination of two solutions. What can we say about those two linearly independent solutions? Yeah.
So I guess they shouldn't be singular in that region.
Right, they should be analytic, and therefore that means they have a
Taylor series.
Taylor series, that's the key word, okay? So what you're quoting here is the theory of Fuchs, okay? And this is rigorous, and what Mr. Fuchs tells us is that all solutions have a Taylor series about x equals x naught. Okay? So this is guaranteed. This is a rigorous result. This is a theorem. Okay? Fuchs theorem. Okay? All solutions have a Taylor series. Done. I don't have to talk about this anymore because you've worked out Taylor series. So all solutions, any solution to this equation, y of x, has a series of the form sum from n equals 0 to infinity, x minus x naught to the n times a sub n. And when I say Taylor series, this is a convergent series. Okay? Period. End of story. This is called a local analysis near x equals x naught. All solutions are regular at x equals x naught, or analytic. Done. There's nothing more to say. this problem has been reduced to a sequence of trivial problems, namely the problem of calculating the coefficients in the series. And you know how to do that. You plug it in, powers of x. Oh, okay, nothing more to say. Okay. Okay. Second possibility. Okay. Oh, and in this case, okay, in this case, this is case 1, all solutions are analytic, we say x equals, so we say x naught is a regular point. Okay, it's a regular point, meaning that all the coefficients in the differential equation are analytic. Okay, so x is a regular point. Done. Okay, part 2. This is, again, understood at a rigorous level. So, theorem, and this is Frobenius' theorem. He says, suppose A and B, or both, A and or B, are not analytic at x equals x naught. Okay, but suppose that, not both, it's not true that both A and B are analytic. So one of them might not be, or the other might not be, or both might not be analytic. But suppose it's true that x minus x naught times A, okay, but x minus x naught times A and x minus x naught squared times B, and if this were a cubic equation, a third order differential equation, x minus x naught cubed times C and x minus x naught to the fourth power times D and so on. Suppose they are analytic. Okay. In this case, we say that x naught is a, now this is an oxymoron. I've always thought this is stupid, but I'm going to tell you what it's called anyway. It's called a regular singular point. Okay, this is a stupid word, but that's what it's called. It's called a regular singular point. And yeah.
Can you imply that the singularity is removable?
Right. Well, no, it's not removable. This is not a removable singularity. A removable singularity is one in which the function looks singular, but as you approach the point, the limit exists, and you get the same result in all directions. So you define the function at the singular point as having its limiting value, and then so you just remove the singularity. There wasn't really one to begin with. It's like sine of x over x. Okay. This is not, we're not removing the singularity, but we're writing down a more general solution. Okay. What Frobenius' theorem tells us is that one solution, at least one solution, has the form y of x equals the sum from n equals 0 to infinity, x minus x naught to the n times a sub n, but there's a little bit more. Does anybody know? This is not quite right yet.
N plus alpha.
Good, n plus alpha. Okay, and alpha is called, a lot of people call that the index. Okay, and one solution is known to have this form. So this is called the Frobenius series. The Frobenius series is a Taylor series where the Taylor series is multiplied, if you like, I'll put it like this. It's multiplied by x minus x naught to the power alpha. Okay, so this is some number here. Alpha could be a complex number, but there's some number there. And one solution has this form, but this part of the solution, this component of the solution, is a Taylor series. Okay, so it's a Taylor series multiplied by fractional power. And that's called, that's a generalization of a Taylor series called a Frobenius series. But not all solutions have this form. So all solutions to the equation may have this form, or they may be just a wee bit more complicated. Other solutions may have exactly the same form, y of x equals blah, 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 same form, except they may also be multiplied by log of x minus x naught. Okay, and if you had a higher order differential equation, there may even be log squared, there could be log cubed, and so on. Okay, this is what you get if you differentiate with respect to alpha. You would get a log. But the important point is this. What is the radius of convergence of the Frobenius series and of the Taylor series? That's the important point. Okay, how big is the region in which these series converge? The answer is these series converge. So here's the point x naught. They converge out to the nearest singularity of A or B. So at this point, A or B might be singular, and that determines the radius of convergence. Furthermore, you might be a lucky puppy. Okay? Doesn't always happen. It's rare when it happens. But it could well be that the series converges beyond the nearest singularity of A or B. You might be very, very lucky. Okay? But usually, the series, you're guaranteed that the smallest possible radius of convergence is the distance to the nearest singularity. Okay, that's it. I have summarized all that is known rigorously about differential equations. That's it. Okay? But I only considered 2 out of the 3 cases. The third case is neither A or B, or neither 1 or 2. In which case, x equals x naught is an irregular singular point. Okay, and the question is, what do you do? And there is no comprehensive theory. There isn't it. That's it. So what do? We do asymptotics. Okay? So that's the reason why I wanted to show you this equation. Okay? So you're walking down the street and some guy writes this equation on the sidewalk. Okay? You look at the equation, what's the first thing you say? I will put the equation into normal form. Normal form. So I get y prime prime equals y over x cubed. Okay? So in that general sense, A is equal to 0 and B is equal to 1 over x cubed. Right? And now we do the Taylor series test. Is a Taylor series going to work at x equals 0? What's the answer? Okay? Do you all agree it's not going to work at x equals 0 because B is not analytic at x equals 0? Okay, so case 1 is excluded. How about case 2? Okay, well, we run a Frobenius test. Is it true that if you multiply this by x, it is analytic? Of course it's analytic. 0 is an analytic function. Okay. If you multiply this by x squared, is it analytic? No. Okay, we don't have a Frobenius series. You may not believe it, but let's try. Let's assume, by the way, there's one thing I didn't mention. In a Frobenius series, you always assume that A0 is not equal to 0 without loss of generality. Why is that? Suppose A0 were 0. You just shift the index, you pull out an additional power, change alpha, and the first term, and you go to the first non-zero term in the series. What if they're all 0? It's a solution, but it's not a useful solution. right? This is a linear differential equation, and 0 is the solution, but so what? Okay, that's the useless solution. Okay, so let's try, we're stupid and we don't know anything, so let's try a Frobenius series. Does it work? Maybe it works, right? So let's see. Is it true that, could we, suppose we just say, all right, these are just a bunch of theoreticians. Let's try a Frobenius series, a sub n x to the n plus alpha, where a0 is not equal to 0. And let's plug it in. Okay? So if you take two derivatives of this, you get the sum from n equals 0 to infinity, n plus alpha times n plus alpha minus 1, a sub n, x to the n plus alpha minus 2. That's two derivatives. But now I have to multiply it by x cubed. You agree? Multiply it by x cubed. So the minus 2 becomes plus 1. And this is equal to y, which is a sub n, x to the n plus alpha, sum from 0 to infinity. Okay. Now, the Frobenius series is just a power times a Taylor series, and Taylor series are unique. So all I need to do is to shift the coefficients in one of these series, right? So, for example, I could shift in here, I could shift n, whoop, this is n. I can shift n goes into n minus 1. Okay, so I can compare this with this. You all agree? So that would mean that I have to compensate by pushing the limit up to 1. Right? So this is n minus 1 plus alpha, n minus 2 plus alpha, a sub n minus 1, x to the n plus alpha. Okay, so I've shifted n downward in here and shifted the limit upward to compensate for it. And you notice this series begins at 1. And this series begins at 0. So when I compare powers of x, the lowest power of x is n equals 0. And the n equals 0 case says that a0 times x to the alpha equals 0. And therefore a0 is equal to 0. Contradiction. Okay? Because we're always assuming that that the first term of the series, without any loss of generality, this first term is always non-zero. Okay? Contradiction. There's no Frobenius series. What do we do? How do we crack into this problem? This is a very, very, very hard problem. Okay? So, there's no general theory. How are we going to solve this problem? Let's look at the case of a first-order differential equation. Let's consider all three possibilities. Possibility 1, possibility 2, possibility 3. Now, remember, a first-order linear differential equation is going to be solvable, so we can look at the solution and see if we can at least have a guess about what is going on. Just a guess. Because we're completely in the dark here. Okay? So let's look, for example, at the equation y prime equals y over 2. And now let's look at the equation y prime equals y over 2x. And then let's look at the equation y prime equals y over 2x squared. Okay, this is case 1. The equation is written in normal form, and the coefficient function is just 1/2. Got it? Is 1/2 analytic? Let's look at these functions near x equals 0. So can you classify the point x equals 0 for this equation, and that equation? So here, x equals 0, what kind of point is x equals 0? It's an ordinary point, right? That's because the function 1/2 has a Taylor series. Trivial. How about this point? At x equals 0, the function 1 over 2x, does that have a Taylor series? No, it's singular. But if I multiply it by x, does it have a Taylor series? Yes. So this is an ordinary point, or a regular point. Regular point. This is a regular singular point. But this, if I multiply this by x, does it become analytic? No. So this is an irregular singular point. Now let's look at the solution. What's the solution to that equation?
E to the power of x over 2 times the constant.
Say it louder.
E to the power of
Yes?
x over 2.
Good. Very good. Okay. So y of x is e to the x over 2
Plus a
times
constant.
some constant. Okay. Now, does this have a Taylor series? I just want to check to see if Mr. Fuchs was lying to us. Was he lying? Well, does this have a Taylor series at x equals 0? Yes, it does. There's the Taylor series. Good. Just as Mr. Fuchs told us, this has a Taylor series. Good. How about this guy? Can you tell me what the solution is to that equation? Can you think of a function which, when you differentiate it, is the same thing as dividing the function by 2x? What's a function with that property? Say. I thought I heard somebody say. Good. Square root of x. Good. Okay. So y of x equals a constant times the square root of x. Good. This is the general solution to that equation. Very, very good. Is this a Frobenius series? It certainly is. In fact, the index alpha is 1/2, and the Taylor series that's multiplying it. What is that Taylor series? 1. It's just one term in the Taylor series. That's okay. But Frobenius was right. Okay? This is in the general form of a Frobenius series. Great. Okay. Now, there is no comprehensive theory about equations like this, but you can solve this. Can anybody tell me what the solution to that equation is?
E to the power minus plus 1 minus.
Yep.
E to
Did
the
anybody-
power,
Say
e to
again?
the power minus 1 over x.
Not
Over 2.
minus 1 over
2.
2x. That's right. So you just pointed out that e to the minus 1 over 2x is a solution, and of course the general solution would be to multiply by a constant. Okay. This does not have a Taylor series or a Frobenius series. Okay. But this has the form, this has a form of y looks like e to the some function of x. S stands for some function of x. Okay, and this function is a singular function. Okay, so you notice the solution here is very, very singular. This is an essential singularity at x equals 0. That's why it doesn't have a Taylor series or a Frobenius series. Okay, so it suggested to a very famous guy. It suggested to a famous guy about how you might approach a problem like this. Okay, the famous guy, and you know the guy's name. This is back in the very early 1800s, around 1800. It's hard to fix the date, but somewhere between 1801 and 1803. The guy's name is Mr. Green. Okay, he wrote operas. As I understand, he wrote Italian operas under the name Mr. Verdi. Okay, but in England, he was a mathematician, and as you know. Okay, so Mr. Green said, I have an idea. If we're trying to solve this equation, why don't we try a solution? Let's try a solution of the form y of x is equal to e to the s of x. And this, I think, if you had to go back and date it, this is probably the beginning of asymptotics. Now, Mr. Green had no idea about asymptotics. He didn't. Okay, but he suggested maybe you could try a solution of that form. Okay? But, in fact, you can trace it all the way back, it turns out, to Shakespeare. And this is something that you can find all kinds of interesting stuff in Shakespeare, but this can be traced back to Shakespeare. You notice that this is a singular function here. Okay? So, if we were solving this, we expect that the solution is going to come out something like e to the a x to the b, where b is probably negative, because this is a negative number. This is not a rigorous claim, but it's going to be something like this, because we expect s of x is singular, okay? That is, it's blowing up at x equals 0. So I expect b to be a negative number, okay? Now, the point here, the reason I say that is, the reason I say that is that if we were to plug this into that differential equation, you know what's going to happen. We are going to have to calculate, y prime. Y prime would be s prime times e to the s of x, okay? And y double prime is s prime squared plus s double prime e to the s of x, okay? And so if I plug this into that differential equation, what kind of differential equation? What do I get? I get the differential equation x cubed times s prime prime plus s prime squared, s prime prime plus s prime squared is equal to 1. Now, this differential equation, so I've converted this original differential equation into this differential equation. This is a first-order differential equation in S prime. Do you all see that? This is a first, not a second-order equation. It's a first-order differential equation in S prime. In fact, if I called S prime, if I just called that t, then this equation would have the form t prime plus t squared equals 1 times x cubed, right? What kind of equation is that? That has a name. And we talked about it here. Say it again. Riccati. This is a Riccati equation. And so we've made no progress. Okay, because you know a Riccati equation is equivalent to a second-order linear equation. Okay, but Mr. Green had something more to say, which he learned actually by reading some Shakespeare. Okay? What he said was, suppose we calculate, this is S. Okay, so if S is ax to the b, we're imagining S to be ax to the b, right? Then S prime would be x to the b minus 1 times b, right? And S double prime is b times b minus 1 times a times x to the b minus 2. And s prime squared is b squared a squared x to the 2b minus 2. Okay, so this is s double prime, and this is s prime squared. And Mr. Green noticed that if b is negative, which of these is more important as x goes to 0? Which becomes negligible as x goes to 0? Say it again? S double prime. That's right. Because s double prime has x to the power b minus 2. But because b is negative, s prime squared has x to the 2b minus 2. So this is very delicate. It's an issue of 2b or not 2b. Okay? That's the point. Okay? So this is the big one as x goes to 0. This is not. Okay, so what we know is that s double prime is negligible compared with s prime squared as x goes to 0. Okay? So this gives us a clue about how to proceed. So what do? We cannot solve this equation. Hopeless. We cannot solve it. Okay? But asymptotics says that this term here becomes negligible as x goes to 0. So by the method of dominant balance, we expect this term to balance that term, and this term to be negligible, and we replace an equal sign where we can make no progress. There's no progress, can't do anything, but we replace this equation by an asymptotic relation, namely the equation x cubed times s prime of x squared is asymptotic to 1 as x goes to 0. Ha! I could solve that equation. It's only a first order equation. So to solve this equation, I divide both sides by x cubed. Okay, this is an asymptotic relation. It's still true that s prime squared is asymptotic to 1 over x cubed as x goes to 0. Okay, and then I take a square root. And I say that s prime is asymptotic to plus or minus 1 over x to the 3/2 as x goes to 0. And therefore s is asymptotic to, I'm going to integrate both sides, no problem. Okay, is asymptotic to, well, I'll say minus or plus 2 over the square root of x as x goes to 0. Now hang on a second. Hang on a second. When I integrate this, I also get an integration constant, right? So I have to write down plus a constant. Is that correct?
I mean, in asymptotics, we can ignore it.
Of course. Very good. Because this is blowing up as x goes to 0, isn't it? So if I add a constant, it doesn't, it's irrelevant. It can be ignored. So we don't know what s is, but we have an asymptotic approximation to s. Just like that. We cracked into the equation. Okay, now we come to a very, very, very subtle point. And this is really, really important. We know what s is asymptotic to. Right? We know what s is asymptotic to. And remember, we're not looking for s. We want to know y. And y is the exponential of s. So now I have a question for you. If f of x is asymptotic to g of x as x approaches some constant, is it true that e to the f of x is asymptotic to e to the g of x as x approaches a constant? Is that true?
No, because when we divide both of them, we get a minus, not divided.
Not. You
Like
don't mean
we had this condition that the limit of f over g equal 1.
yes.
But if we divide this, we get exponential of f minus g.
Right, right. And f minus g, as I said, this actually, don't be misguided. This lecture may actually be organized, because if you remember, at the beginning of the lecture, I said to you that even though f of x is asymptotic to g of x, the difference between f of x and g of x could be very big. Okay, remember that? It was less than an hour ago, just about an hour ago. Okay, so the question is this asymptotic to this? And you're exactly correct. It might be asymptotic, but it doesn't have to be. This is only true if the difference between f of x and g of x is small compared with 1 as x goes to x naught. Okay. Now, does everybody understand that? This is quite amazing. The one thing that you cannot do to both sides of an asymptotic approximation is to exponentiate it. You can differentiate it, you can integrate it, you can square it, multiply it by something, take the square root. You can do all kinds of stuff. But there's one thing you can't do, and that is you cannot exponentiate both sides of an asymptotic approximation unless you can show that the difference between f and g is small as x approaches x naught. And we don't know that. In particular, do you remember what we just did? What did we just do? On your advice, and I'm afraid to say mine as well, we threw away this constant. And if this constant is there, it would not be true, because a constant is not negligible compared with 1. Okay, and there may be something else as well. Okay, for example, there could be a 1 over the 4th root of x. Okay, or 1 or a log of x, or something like that. And if that's true, it is not true that the difference between this and what the asymptotic approximation, it's not true that that's small. So we're very sad, because we would like to say that y of x is asymptotic to e to the plus or minus 2 over the square root of x as x goes to 0. We would like to say something like this, but it is not true, because it turns out that the difference between s, which we don't know exactly, we can never know s exactly, but as you're going to see, the difference between s and 2 over the square root of x is not negligible compared with 1. So we cannot exponentiate both sides. There will be something else. Not necessarily always, but in this case, there is something else. However, we can say that this is the controlling factor of the asymptotic approximation. We have learned a lot. So tomorrow, I'm going to complete this problem. I don't want to get halfway into the problem. I don't want to rush this, because this is very interesting. But this is called the controlling factor of the asymptotic approximation to y. And we now know a lot. We know that the solutions to this differential equation here, this is the differential equation that we're trying to solve, we know that roughly speaking, we know that y of x can have two possible behaviors. It could look roughly, not asymptotic to, but roughly like e to the 2 over the square root of x as x goes to 0. Or it could look roughly like e to the minus 2 over the square root of x as x goes to 0. Two different solutions. It's a second order differential equation. What do these solutions look like? Well, one solution, here's x, as x goes to 0 over here. One solution is blowing up like crazy. One solution is going like that. And that's the reason why it doesn't have a Taylor series. Okay? And the other solution is going to 0 exponentially fast. The other solution is coming along and it's dying out exponentially fast as x goes to 0. Neither of these two solutions have neither has a Taylor series or a Frobenius series. It is a new kind of representation. Okay? And this is typically what you discover from any differential equation. So, do you understand what happened historically? This is how I want to conclude. In mathematics, first people looked at their fingers and they said 1, 2, 3, 4, 5, and they discovered the integers, right? And then some guy went to war and someone chopped off his hand, right? And he said 0. Okay. And then people wrote down equations like x plus 5 equals 0. And they were forced to the negative integers. The only way to write down a solution to this equation is to add to your number system the negative integers. And then they took integers, took these integers and made new kinds of equations like 4x plus 5 equals 0. And now x is minus 5/4, right? So they were forced to include the rational numbers. And then they wrote down equations like x squared equals 2. And they were forced to add the irrational numbers to the number system. And finally, they wrote down, x squared plus 1 equals 0. And they were forced to add the complex numbers. It's forced. Okay? Now, the same thing has happened to us. We begin by constructing functions f of x. Okay? Then we say, you can define a function as the solution of a differential equation, right? And so you can write down, y prime plus f of x, y is equal to 0. And you can solve this. And that, you can put in any of the known functions here, functions that we understand, functions that have Taylor series, the Frobenius series, and so on, and you get new solutions. But you can also, using simple functions, you could write down an equation like x cubed y prime prime equals y, like the equation we were studying today. And when you try to solve this, of course the solution is a function, but the usual ways that we have of representing functions don't work. And we're forced to a new way to represent the function. Let me just tell you the final answer, because I don't want to leave you in suspenders. Okay? In fact, y of x has a representation. I cannot write down what y of x is equal to, but I can write down what y of x is asymptotic to. And it's asymptotic to e to the plus or minus 2 over the square root of x. That's the controlling factor, the most rapidly varying component of the asymptotic approximation, times x to the 3/4, which we're going to discover pretty soon, times a series, which is an asymptotic series in powers of the square root of x. So a sub n x to the n over 2. Not a series in powers of x, but series in powers of the square root of x as x goes to 0. And we're going to discover that this series is a divergent series. So divergent series are forced upon us. This is the only way to represent the solution. We don't have a convergent series representation. We're forced to accept in our collection of ways of representing functions, we are forced into studying a divergent series. And this is an asymptotic series. You cannot get away with it. You cannot get away from it. You have to admit that some answers to some problems, the answers are going to come out in the form of a divergent series. And I'm going to show you the rest of the analysis next time. Okay? And then we have to learn how to sum that series. And actually write down the answer. We want to, why do you write down a series? You write down a series to know the approximate answer, and we're going to have to sum that series. And to do so, we're going to use Padre. Okay? Okay? So are you getting the pieces falling together? Yeah. Okay, good.